The limit is the basis for one of the fundamental concepts of calculus, the derivative. The derivative occurs throughout calculus problems concerned with rates of change and thus has applications in many fields of study. In this section, we begin with equivalent definitions of the derivative given in terms of limits that can be applied to any function. We then look at some simple rules that allow us to find derivatives without directly evaluating limits. We also consider some basic properties of the derivative and its notation. The most common notation for the derivative f of x is going to be this one right here, which is read as f prime of x. This little mark means prime. That is the first derivative of the function f of x. The second derivative of the function f of x is read f prime prime of x. And so forth, and so on with f prime prime, prime of x, and whatnot. We know that in the equation y equals mx plus b, the slope is m. Knowing that the derivative is essentially the slope of an equation, we can find that y prime in this is simply m. We can then apply this to real-life problems with real numbers. For example, if the function f of x is 3x minus 7, f prime of x, the slope or the derivative, is 3. Likewise, here it is negative 4, and here, though we don't see it, there is a 1, therefore the derivative is 1. The power rule is a way to find derivative that comes very handy. In the function f of x equals x to the n, the derivative can be found by multiplying x by the n, nx, and then subtracting 1 from the power of x. This seems a little confusing, but is illustrated better. For example, if f of x equals x cubed, we can find f prime of x by taking n and bringing it down, making that 3x, and then subtracting 1 from the number. So the derivative is 3x squared. Here are some more examples. In this one, we take the 2 down, and we find that by subtracting 1, it is just 1, therefore the derivative is 2x. Here, we take the 3, multiply by the x, and subtract 1, making it 3x squared. We can keep doing this even in powers as high as 100, making this 100x to the 99th. Derivatives can also be found of functions that are not whole numbers. For example, this function, the square root of x, can be written as x to the 1/2, a fraction. We can solve this and find f prime of x the same way, where x prime of x is 1/2 x. What is 1/2 minus 1 equaling negative 1/2? Therefore, it is 1/2 x to the negative 1/2, or 1 over 2 root x. This theorem continues the property we found in the power rule. For example, if f of x equals cx to the n, you just multiply n by c and subtract 1 from n. For example, f of x equals 5x cubed, you multiply 5 times 3, making this 15, and then x, subtract 1, is 2. Therefore, this is the derivative. A special note to be careful of: not every continuous function is differentiable. However, every differentiable function is continuous. This occurs because of cusp points. A cusp occurs if f is a continuous function, but from one side f prime of x approaches infinity, and the other side f prime of x approaches negative infinity. This is illustrated with this graph. We can see here that from one side, the slope of the graph is positive, and the other side the slope is negative, making one side of the graph f prime approach infinity, while the other side approaches negative infinity. This results in a cusp point right here. A few more things about notation for derivatives. We have already seen that f prime of x, f prime prime of x, f prime 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 of x can be written like this, but it can also be read as y prime prime, and y prime prime prime. Furthermore, you may also see derivatives dy over dx. This means the derivative of y in relation to x. This d squared y over dx squared, it's not really squared, but it's written in between the d and the y so that the 2 here and the 2 here do not get confused with powers. Same with 3. But this is also read as the second derivative of y and the third derivative of y.